So, you probably won't have any experience with most of these, maybe a couple. Okay, so example 1. On a certain route, an airline carries 6,000 passengers per month, each paying $200. A market survey indicates, so they do a little survey, and they find that for every $1 increase in the ticket price, the airline loses 100 passengers. So they figured out kind of an average sort of thing. Truthfully, they probably upped the prices by $50 and saw what, the effect was on their number of passengers, and then kind of averaged it out. So on average, every dollar increase, they lose 100 passengers. So the way I wrote this first example sort of breaks down the process for you. Really, it will be a larger question than this. But the first part is to express the number of passengers per month as a function of the ticket price. So our number of passengers as a function of the ticket price X. Okay, so N is our number of passengers. And what is that based on the ticket price? Okay, so currently, what's the number of passengers per month? 6,000. And then how is that 6,000 changing based on the ticket price? Right. We lose 100 passengers for every dollar over 200. Is that fair? So what would that look like? So we lose 100 every time our dollar amount is over 200. So if you take your ticket price X and subtract 200, so this is X dollars minus $200. So in other words, if my ticket price was $201, 201 minus 200 would be $1 over, which would have lost me 100 passengers times that one. If it was $202, then I'd be $2 over, so I'd lose 100 passengers twice because I'm $2 over. Yes? Does that make sense to you guys? Okay, so there's our number of passengers as a function of the ticket price. The airline's monthly revenue for the route is the product of the number of passengers. So let's take this slowly. The revenue equals the product of the number of passengers, so N, times the ticket price, X. Does that make sense? Right? The amount of money the airline's going to bring in is your number of people times however much each of them is paying. So that should make sense. But they want us to express this revenue as a function of only X. So in other words, we need to substitute this N out. Are you with me? Take out the N, so I'm gonna express this just as a function of X. I can take out the N and replace it with this. Before I do that, can we simplify this up a bit? So if I make this 6,000 and then distribute my negative 100, and then 6,000 plus 20,000 is 26,000. So 26,000 minus 100x equals 26,000 minus 100x times x. There's my revenue. So my revenue equals, do I want to distribute? Sure. 26,000x minus 100x squared. Okay, I'm going to give you an easier way to do a problem like this. Okay? This is the way I just did is sort of the way the book presents it. I don't love it. So really the reason we're going to be doing this is to figure out how to maximize our revenue. So we want to make the most money possible. If I look at this revenue equation and look at a graph of it. Let's see, you don't need to do this, just watch, just play along. But it's important that you understand what's actually happening here. So 26,000x minus 100x squared. And of course, if I have a standard window, I don't think I'm going to see much, right? So what does X stand for again? Ticket price. Right now I'm seeing negative $10 to $10. Is that logical for ticket price on an airplane? No. We're starting at $200. So ticket prices would, a realistic domain would be 0 to 300 bucks, maybe. And I'm just going to 300 knowing that we're starting at 200, so that gives me a little leeway on the upper side. The Y is our revenue. What is the current revenue if I have 6,000 passengers each paying $200? What's 6,000 times 200? 12 with how many zeros? 5. So if I look at a revenue from 12 to 5 with 5 zeros, 1, 2, 3, 4, 5 is 1,200,000. Yes? But that's what the revenue currently is. I'm trying to get a maximum revenue. So maybe I'll go up to 2 million just to see what this looks like. Okay, so being able to choose an appropriate window so that we can make sense of this. So here is the dollar amount of the ticket, and here is the overall revenue. We would want our revenue to be at the very maximum, yes? Right? If your ticket price is too low, you're going to sell out your seats pretty quickly and not make that much money. So we charge more. But if you charge too much, some seats aren't going to be filled because, well, people can't afford it, right? So we got to find that sweet spot. We want to maximize our profits, our revenues, by finding the perfect ticket price to maximize our revenue, which would be the vertex of your parabola. So if I do second trace and search for my maximum, left bound, right bound, enter, my perfect ticket price would be $130, it looks like. Interesting. So we're paying too much. Right now we're charging too much. We're losing passengers and not filling seats because the ticket prices are too much. Our best ticket price is $130, and our revenue under that sort of situation would be $1,690,000. Yes? Because right now we're only making $1,200,000. Does this make sense? Okay? And if you go above $130 per ticket, we'd probably start losing money. So right now, we're like in here somewhere. We're charging $200 and making less because of it. Does this make sense? Okay, so that's the conceptual of what's going on. Let me kind of make this easier for you. We're going to come up with that equation in, I think, what makes more sense, an easier way. If that kind of dumbfounds you, I understand why. So the way I like to present this is currently, here's our revenue. Our revenue is 6,000 passengers. This is my passengers. Times $200. And that's my price per ticket. That's the current revenue situation. And then after these surveys, things change. And what we just found out, what they explained to us, is that every time we increase the price by $1, so X is now going to stand for the number of times we increased by $1. Okay? Every time we increase by $1, the effect is we lose 100 passengers that X time. Okay? So if I plot this graph, I'm going to get a different graph than this. These aren't the same function because X is standing for something different in both cases. Here, X is standing for the number of times we increase the price by $1. Here, X was standing for the actual ticket price. Now, we figured out to maximize our revenue here, we got this point, which meant $130 per ticket with $1,690,000 in revenue. Okay? Price per ticket in revenue. This graph is going to show us something different. Our X is not the price per ticket anymore. I haven't defined it that way. I've defined X as the number of price changes, like however many times we're going to increase or decrease by $1, and then this is still revenue. So when I plug this into my calculator as a function to look at, 6,000 minus 100x times 200 plus x. Now my window should be a little bit different because x is the number of price changes. It's not the price of the ticket. So if I go to my window, it does make sense to look at negative x's because that would be decreasing the price up to 50 times by $1, or maybe increasing up to 50 times. So we'll see what that looks like. Okay, we have part of the parabola. I think we're missing more of it that way, yes? So if I go to like maybe decreasing the price up to $200 in either direction, there's a nice parabola. So our maximum profit is going to be here. Second trace, maximum, left bound, right bound. What are we going to get? Because we should already know the answer. We know that the price is $130 that we should be charging. So you tell me, how many times is that decreasing it by $1? 70 times. So I'm going to guess that this is going to be at negative 70, comma, the same maximum revenue number. Should be. Negative 70, same maximum revenue. Does that make sense? So our X here tells us, okay, X is negative 70. That's how we maximize this. So if X is negative 70, then we've actually decreased the price by $1 70 times, making each ticket 130 bucks. And if you wanted to figure out our number of passengers under that situation, 6,000 minus 100 times negative 70 would increase our number of passengers to 13,000. So you're selling for cheaper, but you have more passengers. Do you see how they're both giving us the same information? But I tend to think that this presentation is easier to kind of write the equation for than this one was. What do you think? Does that make sense? But you have to know in this case what your X stands for, and that's the number of price changes. So any follow-up question that they might ask, like what is the price per ticket that we should charge, we would just plug our negative 70 into there and come up with a new one. How many passengers will we reach? Just plug your negative 70 into there and get your number of passengers. So kind of knowing how to use your answer to use the X that we got to answer the appropriate questions. Okay? Does that make sense? If we have time, we'll do another one of those. Okay, exercise 2, switching gears. A machine produces open boxes using square sheets of metal measuring 12 by 12 on each side. 12 by 12. There's our square sheet of metal. The machines cut equal sized squares from each corner. So we're going to cut squares out of each corner. Can you visualize this? I'm going to take a rectangular sheet of paper and show you. But what's essentially happening is you have a piece of paper we're going to cut corners out. Whoops. Do you like when I model for you? This is what the factory's going to do. And then this is going to turn into a box when we fold these up. Does that make sense? Can you see that? Okay, so that's what's happening. I'm going to save that for my later classes. Then it shapes the metal into an open box meaning there is no lid, by turning up the sides. Express the volume of the box in cubic inches as a function of the length of the sides of the square cut. So the squares cut from each side are x by x. We don't know, right? We don't know what that dimension is going to be. But kind of visualizing, maybe I need this back. The volume of the box is length times width times height, yes? So what is the length of this box? 12 minus 2x, very good. It used to be this whole length, 12, but we cut off x there and we cut off x there. So it used to be 12, we cut off this x, we cut off this x. So the length is 12 minus 2x. What's the width? The same, 12 minus 2x. And what's the height? Just x. So here's an equation that's going to be used for the volume. Okay? Now let's talk domain. If x is our size of the square we're cutting off, what are the possible values for x that are allowed? Anything less than 6? Why do you say that, Josh? Right, so if you ever made this as big as 6, you would have taken 6 from this side and 6 from this side, and then you'd be out of your three-dimensional box. So it can't actually be 6, so Josh said anything less than 6. What else? What's the smallest size that you could take? Well, you could do a half. Right, 0, but it can't equal 0. You can't actually cut off 0 because then you wouldn't have anything to fold up. You wouldn't have a box. But anything up until 0. Okay? So now if we wanted to figure out what size corners we should cut in order to maximize the volume, again, we would look at the vertex of this, it's going to be a cubic function, isn't it? Let's see what happens here. So 12 minus 2x, oops, squared, right? I got 2 of those, times x. And our window is 0 to 6 is all we're looking for, right? That makes sense? Can't do anything outside of that. Our volume, what's an appropriate volume? But just let's get in the ballpark. Let's pretend x was 2. So this would be 12 minus 4. 8 times 8 is 64 times 2 is 128. So maybe I'll go like 0 to 500 just to see what happens for our volume. Do you see what I did there? I mean, it's not exact. 500 might be way too much. It might not be enough. But at least I know that one potential volume is 200. So it's got me in the right range. At least I'm not in the 2 million. So if I graph this, I want to maximize. Now, yes, the entire function is a cubic polynomial. So it probably goes, we know about end behavior, right? It goes up, it comes down, and then it probably goes back up. But then by that point, it'll be out of our domain. Does that make sense, Adam? You were worried about it, weren't you? I was a little worried too when I realized, oh shoot, that's a cubic. So to find the vertex of this, to maximize, we just do your maximum, left bound. Do you guys know how to find the maximum on your calculator? Right bound, enter. 2, 128. So the way to maximize would be to only cut 2 out. so that your dimensions, oh, isn't that funny? That was my hypothetical. 12 minus 4, 8 times 8 times 128 happens to be. That's a complete coincidence. I didn't know that. I'll make sure I don't pick a hypothetical of 2 in my later classes today. But that got us our maximum volume. Maximum volume when x equals 2. Volume equals 128. Okay? So you'll be asked to maximize. I know this particular question didn't, but you'll be asked to maximize and minimize things. All right? How do you feel about that one? Is it making sense? Okay. This might be a little more familiar. You have 140 yards of fencing to enclose a rectangular garden. Express the area of the garden as a function of one of its dimensions, x. So, what do you want to call x? The length or the width? I don't care, Jalen, pick one. The length, x and x. So, how are we going to, what are we going to do to reference the width then? I'm going to do this the long way because I'm going to guess that some people wouldn't follow if I just jumped right to the answer. So if I call that y, I know because of my 140 yards of fencing that 2x plus 2y has to equal 140, right? I don't want two variables though, so I need to get rid of this y. So I'm going to solve this for y. Divide both sides by 2, I'm going to get 70 minus x. That's really how our width should be represented, 70 minus x, so that we're all in terms of the same variable. It now wants our area, A, as a function of x. So the area formula is obviously length times width, so that's x times 70 minus x. And there's our quadratic that we will maximize to figure out how we should create this field or whatever it is, this garden, with that amount of fence and making the maximum amount of area. So x times 70 minus x. Our window, obviously x. What's an appropriate domain, would you say? About Lily W. What do you think an appropriate domain would be? Okay, good. I'm sure we'll see what we need to see in that window. Might be a little much, but that's okay. How about our area? What's an appropriate range, do you think? Alyssa? What'd you say? 300? How'd you come up with that? Well, think of a hypothetical x. Make up an x. Make up any old x. Give me an x number. 20. So if x was 20, 70 minus 20 is 50 times 20. 50 times 20 is what? 1,000. So I think that you're, what'd you say, 200? 300 is probably a little small. I'm going to go from 0 to a couple thousand, just to make sure I surpass my hypothetical. And it still might not be enough, but it is, okay? And then we can do second trace, maximum, left bound, right bound, to figure out how big we should make this rectangular garden. 35 should be our x, which is going to give us an area of 1225. So x should be 35, which means our dimensions would be 35 by 35, right? maximize your area, and in that situation your area would be 1,225. Good? Okay, we have a soft drink can that's a cylinder. Is to have a volume of 12 fluid ounces, approximately 22 cubic inches. So there's our volume. First of all, cylinder volume. What's the formula for the volume of a cylinder? Area of the base times the height, and what is the area of the base shape for a cylinder? Circle. So pi r squared is going to give us the area of the base times the height. So there's your volume formula for a cylinder, which you need to know. Express the surface area of the can as a function of the radius in inches. Okay, surface area. You know that formula? So think about a cylinder. What's that? So think about a cylinder. Look over here. This is going to be a beautiful demo as well. Okay? If you were to cut down the side of a can, well, first of all, you got the top and the bottom to worry about as surface area, right? A circle, pi r squared, and another pi r squared, right? So first of all, we have 2 pi r squareds for the top and the bottom. But it's this that's an issue, right? The outer surface area. Okay? If I were to cut down the side of this and unravel a cylinder, what shape does it become? A rectangle, which the area is just length times width, right? In terms, look at this length right here. From the cylinder, where did that come from? The what of the circle? Circumference. So that's 2 pi r, right? And where did the other dimension of the rectangle come from? Right? The height of the cylinder, right? Here's the height of the cylinder, becomes the height of the rectangle. So this is 2 pi r times h. Does that make sense? So plus 2 pi r h. So they're telling us that the volume is to be 22 cubic inches. So if I go and plug that in for volume, that brings this a step further. And they want that surface area as a function of the radius. Right now, the surface area is a function of 2 things, right? It's a function of the radius and the height. They want it just as a function of the radius. So we need to get rid of the h. How do we do that? We solve for h over here, right? So that we can substitute it in. So if I divide both sides over here by pi r squared, h equals 22 over pi r squared. Now I can use that to plug in over here. So my surface area is going to be 2 pi r squared plus 2 pi r, take out the h, and plug in 22 over pi r squared. And simplify. What cancels? Your pi, right? Your r, this r cancels with one of the 2 of those. So it ends up being 2 pi r squared plus 44, 2 times the 22, over the r. And there is your area, your surface area, in terms of just the radius. Was that fun? We'll get to a point in the year where we'll stress again these formulas once we get into calculus, but you should know, make it a point to memorize the volume and surface area of a cylinder if you have not already, which you probably haven't because in geometry it was on your reference sheet, so why would your teacher ever have made you? It wouldn't, right? The area of a circle, for God's sake, is on the reference sheet, which I'll never understand, but hopefully we know that. Okay. We inherit $16,000 with the stipulation that for the first year, the money must be placed in 2 investments expected to pay 6% and 8% annual interest respectively. So the first account's paying 6%. Second account's paying 8%. Express the expected interest as a function of the amount of money invested at 6%, X. So X of these dollars, we don't know how much, but X of these dollars is invested at 6%, okay? So we're writing an equation for the expected interest. So the interest equals, we're making 6% on the first account that contains X dollars. Plus, we're making 8% on the rest of the money. So here's your 8%. How do we express the rest of the money? Winter? 16,000 minus X. Good. Okay? If you have $16,000 total and you already put X of it in that, then the remaining, whatever's left over, is in the 8%. And then you would just simplify that. Okay? And the last one. Sketch the graph of this parabola, 1 minus x squared. So first of all, parent graph is a parabola. Then what's the first transformation on the parabola? Vertical reflection, because of the negative. So it'll be facing downwards. And then what's the 1 do? Shifts it up 1. So your vertex is going to be here. Are you guys, I'm sure some are and some are not, okay with how to figure out where the points are on a parabola as long as it hasn't been stretched or compressed? Like, are you aware that from the vertex to the next set of points, it's just a kind of a slope of down 1 over 1, and then the next one is down 2 over 1, and then the next one is down 4 over 1? Does that make sense? Okay. If you really needed, you could kind of plug in some inputs. And get outputs. But there's the general sketch. So they want us to plot a point on the parabola in the first quadrant, which there's really not much room to do that because it only is in the first quadrant for this little sliver. But let's plot a point XY in the first quadrant. They want us to express the distance from that point P to the origin as a function of the x coordinate only. Well, we know our distance, so first of all, we know our distance formula from yesterday. We also, so we have one coordinate that's xy, the other coordinate that we're finding the distance to is 0, 0, the origin. Okay, so our distance is going to equal the square root of y2 minus y1 squared, so that's y minus 0 squared, plus x2 minus x1 squared, so that's x minus 0 squared. Simplify that, and we have this. But that's the distance in terms of x and y. When it's asking for the distance just in terms of the x coordinate, so we want it just in terms of the x coordinate. How do we get rid of this y? We're going to take out y and replace it with what? What equals y? One minus x squared. So we're going to take out that y and replace it with 1 minus x squared, and then simplify. So that's going to be 1 minus 2x squared plus x to the 4th plus x squared. So that will be x to the 4th minus x squared plus 1. Okay, one quick point I wanted to make about the last one that I wasn't sure we had enough time for, but now we do. When you simplify this function, what is it? Because it's not a quadratic. what will it be? Linear, okay? Which is a little more straightforward then, as far as maximizing. Why is this more straightforward as far as maximizing? What's going to maximize your interest in a case like this? Where would you put your money if you wanted to maximize your interest? Which account? The 8%, right? You would put as much as they would possibly let you into the 8% one, right? So all of it, right? Unless they really force you to use the 6% account, you can put a penny in there. But why wouldn't you put the majority of it in the 8% account? So there's not really much to maximizing that one because it's linear and it's pretty obvious what's going to maximize your profits. Does that make sense? Okay. So your homework is just a sample of these types of problems out of sections 1.10 we're on. And remember, you have a review sheet for chapter 1 that's on there. So if you want to get started on that,